All right, let's get started.
Recording in progress.
All right, hello everyone, and welcome back. We are continuing on with the MHF4U course. This is the grade 12 Advanced Functions University, and we are actually finishing up Unit 1, and this is the review portion. And so we'll be reviewing select topics from lessons 1 to 5. We can't review everything, but we'll review all of kind of the big topics that were covered in each of the units. And so, with that in mind, here are the 5 lessons we're going to be covering. The introduction to logarithms, solving logarithms, the laws of logarithms, real world applications of logarithms, and a small section on understanding radian measure. For the calculators today, I've got the Desmos scientific calculator as well as the Desmos graphing calculator. Both of these will be beneficial. Okay, so example 1, we started off with the introduction to logarithms. So we wish to complete the chart. And so we want to convert these from the exponential to logarithmic form. So recall that if you had something of the form a to the power of x is equal to b, and this was your exponential form, the logarithmic form would be x is equal to log base a of capital B. Okay, so a to the power of x is equal to b is equivalent to the logarithmic form x is equal to log base a of b. And so if we have 5 to the power of negative 4 is equal to 1 over 625, this will be the same thing as, and the key thing to note is you see what the base of the exponential is? That'll be the base of the logarithm, and you're going to be solving for the exponent. So this will become log base 5 of 1 over 625 is equal to negative 4. So the base of the log is the base of the exponent, and you're solving the logarithm equal to the exponent. Okay. Letter B, so the second one here, we have log base 3 of 243 is equal to 5. This is the same thing as 3 to the power of 5 is equal to 243. And these ones are pretty easy to verify using a calculator because you just type into the calculator 3 to the power of 5 to confirm that it equals the exponent or power equals what you would need it to be. Okay. Next one is 9 to the power of 4 is equal to 6,561. This will be equivalent to log base 9 of 6,561 is equal to 4. And it's worth noting again that you don't need to put a bracket around the logarithm, the number involved in the logarithm, but sometimes I feel that it adds clarity, so it makes sense. Lastly, but not leastly, we have log of 1,000 is equal to 3. And remember, if there's no specified base, you can assume that it's log base 10. And so we can write that as 10 to the power of 3 is equal to 1,000. So that's converting between the exponential and logarithmic form. In example 2, we're going to sketch y is equal to 1/4 to the power of x, its inverse, and the line of reflection. And so remember, if you have your function, f of x, or I should just say our function, x comma y, the inverse function, f of negative 1, will be denoted by y comma x. So if we have the x and y values just for the graph of the original function, we can just swap or interchange the x and y components, and that'll give us the inverse. And that's the easiest way to go about that. So we're going to use a table of values to assist us. And so let's go ahead and get this sketched in. And I'm going to leave some extra room in here because I'm going to have my x, I'm going to have f of x, which is going to be 1/4, but then I'm also going to have f negative 1. So do we know x or just standards? So you get we kind of evaluate is calculated. Is and last in the oh, okay. A little bit of an internet surge there. These things happen. Okay, and we're back. So let's go. We're still recording, and we'll go back here. Okay. So again, you just want to be typing, evaluating this function at each of the given values. And so for here, we can just type into our calculator 1/4 to the power of -2. So if we do that, 1/4 to the power of -2. You can see we get 16. The next one will be -1/4 to the power of -1, and that'll be 4. Next one will be, oh, hold on, it's got to share my screen. Okay, we're back. So just to give a quick little review here, so we wanted to sketch y is equal to 1/4 to the power of x, its inverse, and the line of reflection. So for x values, we chose -2, -1, 0, 1, and 2. For f of x values, we chose, we just evaluate our function at each of those points. So in the calculator here, we did 1/4 to the power of -2. The next one would be 1/4 to the power of -1, which is 4, and we evaluate them from there. So 1/4 to the power of 0 is going to be 1. 1/4 to the power of 1 will be 0.25, and 1/4 to the power of 2 is going to be 1/16. Which as a decimal is going to be 0.0625. Okay. And now, in terms of our inverse coordinate, remember this is just going to be y comma x. So we just switch these values. So we're going to have, instead of -2 going to 16, we're now going to have, I'll put these in blue, 16 comma -2. The next one will be 4 comma -1. The next one will be 1 comma 0. Then 0.25 comma 1. And lastly, we're going to have 0.0625 comma 2. So graphing these values, for f of x, their first point is -2 comma 16. So that would be about -2 would be here. We go up to 16, so it'll be about there. Next one would be -1 comma 4, be about here. Next one would be 0 comma 1, 1 comma 0.25, and then so forth. And again, you try to graph these on the line as best as you can. Okay? And we end up having a curve that looks like this. So we will label this our f of x value. We'll color code this. Our inverse will be the x and y value switched. So instead of negative 2 comma 16, we're instead going to have 16 comma negative 2, which would be here. The next point will be 4 comma negative 1. So that'll be about here. Next one will be 1 comma 0. So it'll be about here. Next one point will be 0.25 comma 1. So it's about there. And then we try to get as close as possible and so forth. And so here we can end up connecting our points as such. And so this is our inverse f negative 1 of x. The line of reflection is the equation y is equal to x, and that is going to be just a dotted line down the middle. Okay, so these are a little bit of work, but again, you can evaluate these using just a table is fine, or you can follow along with some of the examples in the book. They do a fairly reasonable job of showing this as well. Okay. Next thing we're going to have a look at is solving some logarithms. And so we want to go ahead and evaluate these. And the best way to go about this is to write these with a common base. And so if we have our first one here, we're going to evaluate these. We have log base 2 of 32. And so we can recall the fact, and I'm going to write this just once, but remember that 2 to the power of 5 is equal to 32. And so we can replace our 32 with 2 to the power of 5. And so we can write this as log base 2 of 2 to the power of 5. Now, using our inverse property, or we can use the power law of logarithms, we know that if you have log base a of a to the power of something, the answer is just that something. So here our answer will be just 5. Okay. For our next one here, what we have is log base 6 of 216 to the power of 3. And so for this one here, what we need to do is to go ahead and express the 216 as a power of base 6. And so recall that if we have 216, that's the same thing as 6 to the power of 3. And so we can rewrite this as log base 6 of 6 to the power of 3, all to the power of 3. So we can go ahead and simplify those exponents down, giving us log base 6 of 6 to the power of 9, which is going to be 9. Okay, so remember to use the exponent laws. You can just multiply those powers together. Letter C, we have log base 3 of 1 over 27. Recall that we can express a fraction, 1 over 27, as 27 to the power of negative 1. And then 27 is merely 3 to the power of 3. And so this will be the same as log base 3 of 3 to the power of 3 to the power of negative 1. And so simplifying this down, our solution is going to be negative 3. So remember, when we multiply these exponents together, that'll give us a negative 3, which corresponds to our solution. Letter D is sort of the generalized base version of this question. If you have log base x of 1 over x, we can write this as log base x of x to the power of negative 1, which simplifies down to just being negative 1. Okay, so that's it. So here we were able to evaluate these logarithms, and the method that we used was a common logarithm. Or I should more accurately say this as a common base. Okay, the same way we were able to evaluate exponentials if we were able to set both sides equal to a common base, you can do the same thing with these logarithmic statements. Okay, number 2, we actually got to solve for x now. And so here we've got log base 3 of x is equal to 4. So using the equivalent exponential notation, this is the same thing as 3 to the power of 4 is equal to x. And if you're not sure, 3 to the power of 4 is going to be 81. And that'll be our solution. Okay. Letter D, same kind of idea. Log base 5 of x is equal to negative 3. So we can rewrite this using exponential notation as 5 to the power of negative 3 is equal to x. So remember, if you have a negative exponent, you have to take the reciprocal of this. So this is the same thing as 1 over 5 to the power of 3. 1 over 5 to the power of 3 is equal to x. And if you type into your calculator, 5 to the power of 3 is 125. So this will be 1 over 125 is equal to our x value. Okay. If you would like to, you could also use the calculator to evaluate 5 to the power of negative 3. Just make sure you get the fraction component for that in order to ensure your solution is correct. Okay. What about letter C? We have log base x of 1 over 216 is equal to negative 3. We're going to treat this the same way. So we'll convert this to its exponential equivalent. So we'll rewrite this as x to the power of negative 3 is equal to 1 over 216. 1 over 216 is the same thing as 1 over 6 to the power of 3, because we saw that one from earlier. We can then rewrite this as x to the power of negative 3 is equal to 6 to the power of negative 3. And if you notice here, the exponents are the same, so we can equate the base. And we can see that we have that x will actually just be equal to negative 3. This kind of question doesn't come up too often. The textbook, I believe, might not even have an example of this, but I would be remiss if I did not show you how this kind of question worked. We do have a stipulation because the base of the logarithm is the exponent. We do stipulate that x has to be greater than 0, but unequal to 1 is our only stipulation here. Okay, so if we got, say, for example, a base that was negative, that wouldn't make any sense. Letter D here, we've got x is equal to log base 3 of the cubed root of 81. So remember, when you have a radical base, write that using a rational exponent. So this will be x is equal to log base 3 of 81 to the power of 1 over 3. And so if you have, say, the nth root of a, that's the same thing as a to the power of 1 over n. Okay, we're using that rule. 81 is the same thing as 3 to the power of 4. And so we can have x is equal to log base 3 of 3 to the power of 4 to the power of 1/3. Simplifying down the exponents, we multiply these together. 4 multiplied by 1/3 will be 4/3. And so x will be equal to log base 3 of 3 to the power of 4/3. And simplifying this out, we get x is equal to 4/3. And so this was the circumstance where we were able to either directly solve this by converting to the exponential equivalent, or we might have had to equate the base. And sometimes we just have to work with the logarithm directly and get a common base. Now, it's worth noting that if you so wished, you could have transformed this into its exponential form. If you did that, what we would end up with is 3 to the power of x is equal to the cubed root of 81. And then from this point, using a similar exercise as before, this is going to be the same thing as 81 to the power of a third, which will be 81, not 81, 3 to the power of 4 to the power of a third. And so you'd end up with the case that 3 to the power of x is equal to 3 to the power of 4 thirds. And then from here, this is exactly the same result that we had from earlier. So you could have, if you so wish, use the exponential form as well. You would have had the same conclusion in the end. And in fact, it is worth mentioning that solving these in more than one way is actually a good idea, because again, the mistake that I see students often make with these is that they forget to transform them back into its exponential form. Okay, let us continue. Simplifying using the laws of logarithms. So recall that if you have, say, log of x plus sign log of y, where the bases are the same, this is the same thing as log of x, y. And if you have log of x minus sign log of y, this is the same thing as log of x divided by y, regardless of the base. And if you have log of x to the power of n, this is the same thing as n times the log of x. Okay, so we're going to simplify the following using the laws of logarithms. So we can't just type this into a calculator. We actually need to go ahead and show some steps. So for letter A here, we have log base 3 of 135 minus log base 3 of 5. So using the quotient law, we can rewrite this as log base 3 of 135 divided by 5. Here it's okay to use a calculator for 135 divided by 5. You can see that it's equal to 27. So this becomes log base 3 of 27. And we've actually answered this question already. I believe we answered the 1 over 27 from earlier. But 27 is the same thing as 3 to the power of 3. So this will be log base 3 of 3 to the power of 3, which will just be 3. A lot of 3's, but not so bad. Okay, what about letter B? Well, we have the log of the square root of 10. Okay, so we can write this as log of 10 to the power of 1/2. And from here, we already know the answer should be a half, but the question stipulated that we use the law of logarithms. So we're going to bring down the 1/2. So this will be 1/2 times the log of 10. Log of 10 is equal to 1. So you end up with 1/2 multiplied by 1, which is merely 1 over 2. Okay. I also would not fault you if you just immediately said that if you had log of 10 of 1/2, this is equal to 1 over 2. But the question did say, make sure to use the laws of logarithms, and this is the best way to ensure we do that. Okay. There's nothing, we can also evaluate more complicated expressions. So instead of just saying log plus a log or log minus a log, we could instead have something like log base 6 of 54 plus log base 6 of 2 minus sign log base 6 of 3. And so we can combine these all into one step. So we can write this as log base 6 of, so this is, we have a plus sign here. So log base 6 of 54 plus log base 6 of 2. So it's going to be 54 times 2. And we're minusing off log base 6 of 3. So we're going to divide this by 3. So it was possible to do this all in one fell swoop. Simplifying this down, if we have 54 multiplied by 2 divided by 3, you can see we get 36. So this is equivalent to log base 6 of 36. 36 is the same thing as 6 to the power of 2. And so we get 2 as a solution. And keep in mind, we were keeping log base 6 for all of these things. And so log base 6 of 54 plus log base 6 of 2 minus log base 6 of 3 was equal to 2. Okay. Letter D, the most complicated looking expression. We have here log base 8 of 2 plus 2 log base 8 of 2 plus 1/2 log base of 16. So our first step here is to use the power law of logarithms to move the number in front of the log up back to the argument. And so this is going to give us log base 8 of 2 plus, now instead of 2 log base 8 of 2, we instead have log base 8 of 2 to the power of 2. And instead of 1/2 log base 8 of 16, we have log base 8 of 16 to the power of 1/2. Okay, so let's simplify down these exponents. So log base 8 of 2 stays the same. Nothing changes there. Log base 8 of 2 to the power of 2 becomes log base 8 of 4. And 16 to the power of 1/2 is the same thing as the square root of 16. So we end up getting log base 8 of 4. Using the product law of logarithms, we can rewrite this as log base 8 of 2 multiplied by 4 multiplied by 4. So 4 times 4 is 16, times 2 is going to give us 32. So this becomes log base 8 of 32. Okay. Now, usually for this kind of question, this is about kind of the limit of what we want to be able to do. We can go a little bit further if we had to, but the book wouldn't ask you to simplify beyond this. So this is what we would consider to be done. Okay, because it's quite difficult to write 32 as a base of 8, insofar as a question from the textbook's not going to ask you to do that. So usually simplifying it down as a single logarithm would be okay. Okay, let's continue on. So for example 2 of, or number 2 of example 3, it says it's asking us to solve and solve these questions, identify and reject any extraneous roots. And so we have 2 minus log base 4 of x minus 11 is equal to 16. So the goal for this is to isolate all of your variable terms on one side of the equation. In this case, we have an x minus 11 that's subject to log base 4. We'll have to convert this to its exponential equivalent and then solve. And so doing so, we have 2 is equal to, now negative log base 4 of x minus 11 becomes positive log base 4 of x minus 11. Next thing we do is convert this to its exponential equivalent. So this becomes 4 to the power of 2 is equal to x minus 11. And so x will be equal to 4 to the power of 2 plus 11. So on your calculator here, if you take 4 to the power of 2 plus sine 11, you can see x is equal to 27. Okay. So here in the first step, we moved the log over. On the next step, we use the exponential equivalent. On the last step, we isolated x. And then we simplified. Okay, a lot of these questions we're going to be looking at look like this. And now the only thing we need to see is that we have to reject an extraneous root. We're going to be okay here because if we were to insert a 27 back into the original expression, 27 minus 11 is positive 16, so we're not going to run into any issues here. If we were to subtract those answers and we'd end up with a negative solution, then that means this had no answers to begin with. We would consider it extraneous. So there are no extraneous solutions, and so we will just circle our answer to confirm that this is the right choice. Okay, let's continue on. For letter B, we have log of x plus 2 plus sign log of, in brackets, x minus 1 is equal to 1. And so just like we solved this with the numerical example, we want to go ahead and combine the logarithms together. So log of x plus 2 plus sign log of x minus 1 is the same thing as log of x plus 2 times x minus 1 is equal to 1. Now, if you remember, this is, since there's no base, it's log base 10. And so we can rewrite this as x plus 2 times x minus 1 is equal to 10 to the power of 1. 10 to the power of 1 is going to be 10. Expanding out the first expression, x plus 2 times x minus 1, this becomes x squared plus x minus 2 is equal to 10. So x times x is x squared. 2 times negative 1 is negative 2. 2 plus negative 1 of the x variety is positive x. Minusing that 10 over, we get x squared plus x minus 12 is equal to 0. Next, we got to factor this. So what two numbers multiply to make negative 12, but then add to make 1? So those numbers are going to be positive 4 and negative 3. And so here we have solutions of x is equal to negative 4 and x is equal to 3. Now, if we're going to check our answers here, if you look up here, if I try inserting negative 4 into the equation, I end up with negative 4 plus 2, and that's already going to be a negative number. And so what that means is that our negative 4 is going to be extraneous. So we will just indicate that this expression is, or this solution is extraneous. Okay, what about 3? Well, if we insert 3 into here, 3 plus 2 is positive, 3 minus 1 also positive, so this answer is okay. So we'll go ahead and circle the solution, and that's going to be our answer. Okay. Letter C, we have log base 5 of 2x is equal to 1/2 of log base 5 of 9. And so just like before, what we want to do is simplify the expression. But the first thing we want to do is to bring that 1/2 up to the 9. Okay, so we're going to bring this 1/2 up here. And so we can rewrite this as log base 5 of 2x plus sign log base 5 of 9 to the power of 1/2 is equal to 2. 9 to the power of 1/2 is just 3. So this is equal to log base 5 of 2x plus sign log base 5 of 3 is equal to 2. Okay, now we can combine these into a single logarithm. And we couldn't do that before because we wouldn't know where this 1/2 would go. Because if we tried to combine these right away, the 1/2 might end up, say, outside of the entire expression. And it should not be affecting that 2x term, which is why we needed to simplify down the second exponent first. Okay, so this is equivalent to log base 5 of 2x multiplied by 3 is equal to 2. 2x times 3 is 6x. So we end up with log base 5 of 6x is equal to 2. We now need to combine the exponential form. So we can rewrite this as 5 to the power of 2 is equal to 6x. And so 5 to the power of 2 is just 25 is equal to 6x. Divide both sides by 6, and we end up with a solution of x being equal to 25 on 6, which is not a nice number. So if you try to divide that out, we end up getting this number. And so how do we know our answer is okay? Well, if we take this 25 over 6 and insert it back into the original, we have a 2 times 25 over 6. That's positive. So that means this will work. If you wanted to, you can use Desmos graphing calculator to verify that our solution's correct. So we could write this as log base 5 of 2 multiplied by 25 over 6 plus sign 1 over 2 multiplied by log base 5 of 9. And you can see we get a solution of 2. Now, we could have used the simplified version of this. Instead of 1/2 log base 5 of 9, we could have just used log base 5 of 3. That doesn't change what our answer is going to be. So we end up getting the same thing. I just prefer to use the original because if we made a mistake somewhere in the middle, we might as well compare against the original because the original is where we started. So if you want to check this, you want to make sure that you check your solution against the original equation. Okay, interesting question. I quite like C, but we will have to see it and move on for now. Okay, so example 4, I've got a few and 3, some real world applications. So recall that the general equation for modeling an exponential relation is given by capital P is equal to P naught times B to the power of T over D. Or depending on the situation, you might write this as capital M is equal to M naught times B to the power of T over D, where P or M is the amount over time, P naught or M naught is the initial amount, T is the time typically, and D is the period, how long it takes for the base to apply. So an example might be if you have a black fly population doubling every 7 months, the base would be 2, and the period, D, would be 7. Okay, but A, we've got a bear population. So the bear population increases at a rate of 1.2% per year. If there are 400 bears in a local park, how long will it take for the bear population to reach 500? Okay, so we write down our equation, capital P, P naught, B, T, and D. Okay, we're calling that P is equal to P naught times B to the power of T over D. Okay, so P, how many bears we're going to end up with? Well, that's 500. How much did we start with initially? There's 400 of them. Our B value is the base. So the base is a percentage here. So it's going to be 1 plus 1.2%, which as a decimal becomes 1.012. Okay, so convert that decimal into that percent into a decimal. So that would be 1.2 divided by 100. So we get 0.012, and then you add 1 to it, and that's going to be our base. The time, we don't know how long it's going to take. But this happens per year, so D is going to be equal to 1. So the important fact consideration that year 100% ability and 100 And to know how long. So these questions will give 5 pieces of information in order to solve these. So setting up the equation, we end up with 500 is equal to 400 multiplied by 1.012 to the power of t over top of 1. Okay, so t over 1 is just going to be, that's just going to be t. So 500 divided by 400, that's going to be 1.25, but you can use a calculator to help you if you're not sure. To 1.012 to the power of t, using the exponential equivalent, the logarithmic equivalent. T by 2. And I admit, this is quite a bit of steps that we have to go through, but we did spend the past 3 lessons like practicing the change of base, practicing the writing equations, how to solve these. And in the lesson notes we covered earlier, I showed you about the change of base formula. Okay, so we type this in. So we end up with log and log. So this is going to be log of 1.25, and we're dividing by log of 1.012. So we end up with our solution being that it's going to take, looks like 18.7 years. And we can test to see if this works. So in the original, if we take 400 and multiply by 1.012 to the power of 18.7, or not 187, 18.7, we get 499.96, also known as 500 bears in the park. Number every day, they must be in Pickle Lake. How long until they reach 10,000? And so using our formula here, we would write this as capital P, P naught, our base, the time, and the period. So capital B, how many black flies are there at the end? Well, there's going to be 10,000 of those. How many do we start with? Well, 700. The base, how fast are these growing? We are doubling, so that's going to be 2. T is the time. We don't know how long this takes. And D is the period. So how fast does this happen? It happens every day, so D is equal to 1. So given the equation, capital P is equal to P naught times B to the power of T over D. P is going to be 10,000. P naught is going to be 700. Our base will be 2. T is going to be just T, and this is happening every day, so it'll become T over 1. And just like before, the T over 1 will simplify down to just being T. Dividing both sides by 700, we end up with 10,000 over top of 700 is equal to 2 to the power of T. It's worth noting here we can cancel out some zeros. So 10,000 over 700 is the same thing as 100 over 7. Rewriting this in the logarithmic, T is equal to log base 2 of 100 divided by 7. If you didn't notice that 10,000 over 700 reduces down to 100 over 7, you could just write 10,000 over 700. You get the same answer. Applying the change of base formula, we end up getting log of 100 over 7 divided by log of 2. Okay, so let's type this in. Log, so log of 100 divided by 7 over top of log of 2. We get that the black flies will multiply, and they'll get there in about 3.8 days.
And just like before, you might be thinking, is that realistic? Well, keep in mind, 700 doubles to 1400. The next day doubles to 2800. The next day doubles to 56. So 3.8 days does make sense. Okay. Just in case, because I don't want to take this for granted, the change of base formula says that if you have log base b of a, that's the same thing as log of a over log of b. Okay. Let's see. Letter C, most interesting question. We have chocolatium is back. It has a half-life of 45 seconds this time. If there's a 1,000-gram sample, how long is there until 200 grams is remaining? So instead of P, we'll use M for mass, I suppose. So capital M will equal M naught times B to the power of T over D. And so writing down what we know, capital M, how much is there at the end? Well, there's going to be 200 grams of this left. M naught is the initial value. So how much is there to begin with? There's a 1,000-gram sample. It'll be 1,000. Our base point. How long T is our time? We don't know how long this is in a period. And so writing down our equation, capital N will be 200 is equal to 1 multiplied by 0.5 to the power of T over 45. Dividing both sides by 1,000, we get 0.2. So if you take 200 divided by 1,000, you get 0.2. T over equivalent and over log base 2 of 0.2. Multiplying both sides by 45, we get T is equal to 45 times the log base 2 of 0.2. And applying the change of base formula, we get T is equal to 45 multiplied by log of 0.2 divided by the log of 2. Like I said, a lot of steps here, but it follows roughly the same algorithm as you go through this. So typing this in, 45, not 10, we're not at 10 yet. 45 times the log of 0.2 divided by the log of 2. We get T is equal to negative 104. 104.48. Okay, so this is going to be in seconds. .5. So that answer to me was wrong. But here I've just the piece of 2, which happens sometimes. We'll write this as a log base 0.5, 0.5. And that was judging the reasonableness of an answer, because if my chocolatium bar is disappearing over time, there's no way that I can suddenly take a negative amount of time. That doesn't make any sense. And so we're going to swatch out 2 for 0.5, and we get the positive version, which is going to be correct. So this is going to be 104.5 seconds. To verify this is if this is correct now, if I take 1,000 multiplied by 0.5 to the power of 104.5 divided by
45, we can see we get that 200 number. So we know that we did that correct. And so we can box our answer and we'll be okay. Okay. Last one, and I see we're low on time, but we should be able to get these finished up today. Example 5, we're going to convert the following from degrees to radians. So all we need to do is take this 180 degrees, this negative 240, and this 43, and just multiply it by pi over 180. That's it. So to multiply from degrees to radians, you just multiply by pi over 180. So A becomes just, so 180 times pi over 180 is just pi. Negative 240 times pi over 180 becomes negative 4/3 pi. And again, if you weren't sure about this, you can take your negative 240 divided by 180, see that you get your negative 4/3, and then just tack on a pi. The last one here, we end up getting this 43 pi over 180, which is not really an elegant answer. So we will instead write this in its decimal form, 43 pi over 180, which is going to be 0.75. And at this point, we write radians. It's understood that if you have an angle measure involving a pi, that's understood to be in radians. But if it's just some sort of decimal, make sure to indicate that it's rad. To convert from radians to degrees, we multiply by the reciprocal of pi over 180, namely 180 over pi. And so we're going to take pi over 6, 13 pi over 6, and 2.94, and multiply those all by 180 over pi. And so the nice thing about multiplying by 180 with the pi calculations, because remember those are exact values, the pi just go away. So for the first one here, we just have 180 divided by 6. So that's going to be 30 degrees. For letter B, we've got 13 over 6 times 180. And so if you take 13 over 6 and multiply it by 180, you get 390 degrees. And if you take, the last one here is just 2.94, so you have to multiply it by 180. End up keep them up around you. We've got the little circle to indicate that it's degrees. Lastly, but not leastly, we're going to sketch each angle given in radian measure in standard position. And so for these ones here, you want to just draw out your Cartesian planes. And I just staggered these ones just so that way they look a little bit more reasonable. And we go through this. So standard position means it starts on the positive x-axis. Okay, and we rotate counterclockwise. So pi over 6 pi. This is quadrant 1. 4 pi over 3 is a quadrant 3 angle because it's over pi. So it's between, remember, a quadrant 3 angle is between pi and 3 pi over 2. So this angle will go all the way down into quadrant 3. And this is going to be 4 pi over 3. Lastly, we have negative 2.94. So this is a negative angle. So we're going to go instead of going counterclockwise, we're going to go clockwise now. And so negative 2.94 is also going to be in quadrant 3 because, and the reason for that, and perhaps I'll write these ones in blue. I got to reverse these since we're going the other way now. This is going to be our pi over 2 axis.
pi over 2 is 1.57, and pi is 3.14 if we're on the negative version. And so we're going to be in quadrant, we're going to again be in quadrant 3 because it's a negative angle. And this will be negative 2.94. So we'll say this is negative, and these other two are positive. Okay. And so with that, we finished 30 seconds to spare. That concludes unit 1 for us. And so this is pretty much what the rest of the course is going to look like. I'll go through each of the units one by one. We spend more time on sections that need it. So in the next section, we're going to be spending a lot more time on developing some trigonometry, which is where we're going to go with this. And we have the occasional tech issue, but we try to resolve those as best we can. As always, if you have any questions, comments, or concerns, please feel free to reach out and we'll get back to you as soon as I can. But for now, have yourselves a wonderful day and we'll see you soon.